Let's start with probably the most famous time paradox of all time, the grandfather paradox. Here's how it goes. Imagine you build a time machine. Cool, right? You hop in, travel back to before your parents were born, and you accidentally, or maybe on purpose, I'm not judging, prevent your grandfather from meeting your grandmother. Now here's where it gets weird. If your grandparents never meet, your parents are never born. If your parents are never born, you're never born. But if you're never born, who went back in time to stop your grandparents from meeting in the first place? See the problem? You can't exist to go back in time if going back in time prevents you from existing. It's a perfect loop of logical impossibility. Some physicists say this means time travel to the past is just flat out impossible. Others suggest parallel timelines. You create a new branch of reality where you don't exist, but your original timeline stays intact. And some think the universe has some kind of cosmic protection system that just won't let you do it. Whatever the answer, your grandfather can sleep soundly knowing he's part of one of physics' greatest puzzles. Next up, we've got the bootstrap paradox, also called a causal loop. This one's deliciously weird. Imagine you travel back in time and give Shakespeare a copy of all his plays that you brought from the future. He copies them, publishes them under his name, they become famous, and eventually you find them in a book and bring them back to him. Here's the question. Who actually wrote the plays? You didn't write them. You just copied what Shakespeare published. But Shakespeare didn't write them either. He just copied what you gave him. The information exists, it loops through time, but it has no origin point. It's information without a creator. This happens with objects too. Imagine a watch that's given to you by your future self. You keep it for 30 years, then travel back and give it to your younger self. That watch never gets manufactured. It just exists in a loop, getting older and older forever. There's no beginning to its existence. The bootstrap paradox basically asks, can something exist without ever being created? And if the answer is yes, doesn't that break everything we understand about cause and effect? Sweet dreams thinking about that one. All right, buckle up because we're combining black holes and time travel now. Paradox 3 is the temporal paradox of rotating black holes. According to Einstein's general relativity, if a black hole is rotating, and most of them probably are, it creates something called a Kerr black hole. And Kerr black holes have a really strange feature. They might contain closed time-like curves. In plain English, paths through space-time that loop back on themselves. Here's what that means. If you fell into a rotating black hole and somehow survived, big if, you could theoretically follow a path through the warped space-time that brings you back to your own past. You could, in theory, meet yourself before you fell in. Wild, right? But this creates all the same problems as the grandfather paradox. What if you convince your past self not to jump into the black hole? Then future you never exists to go back and warn yourself. Paradox. Most physicists think that something prevents this from actually working. Maybe the black hole crushes you long before you can complete the loop. Or maybe the universe has some rule that stops closed time-like curves from forming in reality. But mathematically, the equations say it's possible. And that's deeply strange. The math allows for time travel, but reality might just veto it. All right, here's one that sounds like science fiction but is actually proven science. The twins paradox. Imagine you have an identical twin. You hop on a spaceship traveling near the speed of light and zoom off to a distant star and back. Your twin stays on Earth. When you return, you're only a few years older, but your twin has aged decades. This happens because of time dilation, a real effect predicted by Einstein's special relativity and confirmed by experiments. The faster you move through space, the slower you move through time, relative to someone standing still. It's not an illusion or a trick. Your clock literally runs slower. You literally age slower. So here's the paradox. From your perspective on the spaceship, isn't Earth the one moving away from you at high speed? Shouldn't your twin be the younger one? The resolution involves acceleration, and which twin actually changes reference frames, but it still messes with our intuition. Time isn't universal, it's personal. Two people can experience completely different amounts of time, and both are equally right. Reality doesn't have one clock. It has billions. Now on to Paradox 5. Ladder Paradox, also known as the pole barn paradox. This one's a beautiful brain bender. Imagine you're carrying a ladder. Let's say it's 20 feet long, and you're running really, really fast, like a significant fraction of the speed of light. You're running toward a barn that's only 10 feet deep, with doors on both ends. Now, according to special relativity, objects contract in the direction of motion when they move at high speeds. So from the barn's perspective, your 20-foot ladder squishes down to, say, 8 feet. It fits inside the barn. For a moment, both doors could be closed with the ladder fully inside. But here's the paradox. From your perspective, running with the ladder, you're not moving. The barn is moving toward you, and that means the barn is the thing that's contracted. From your viewpoint, the barn is now only 5 feet deep, and your ladder is still 20 feet long. There's no way it fits. So which is true? Does the ladder fit in the barn or not? The answer involves the relativity of simultaneity. Events that are simultaneous in one frame aren't simultaneous in another. Both perspectives are correct, but they disagree on what "at the same time" even means. Reality doesn't have one universal now, mind-bending stuff. All right. Paradox 6. The Andromeda Paradox. This paradox is unsettling in the best way. Imagine two people walking past each other on the street. Let's call them Alice and Bob. Alice is walking toward the Andromeda galaxy. Bob is walking away from it. They're walking slowly, just a few miles per hour. No big deal, right? Wrong. Because of relativity of simultaneity, what counts as now in Andromeda depends on your motion. From Alice's perspective, moving toward Andromeda, right now, in that galaxy, might be a day in their future. From Bob's perspective, moving away, right now, might be a day in their past. We're talking about events that are millions of years away but separated by days depending on whether you're walking forward or backward. So if there is an alien council meeting happening in Andromeda right now, Alice and Bob, just by walking different directions, have completely different moments that qualify as simultaneous with their present. The meeting might have already happened for Bob, but not yet for Alice, even though they're standing right next to each other. This suggests the future might already exist somewhere in space-time. Everything, past, present, future, might be equally real, just sitting there. That's deeply weird. Okay, moving on to Paradox 7, Ritdijk-Putnam Paradox. The Ritdijk-Putnam paradox takes the Andromeda paradox and pushes it even further. It's named after philosophers and physicists who argued that relativity of simultaneity implies something shocking. If different observers have different nows that are equally valid, then the future must already exist in some sense. Think about it. If your now includes events that are in my future, then those future events must already be real. They're just not in my present moment yet, but they exist. This is called the block universe idea, the notion that past, present, and future are all equally real, like a giant four-dimensional block of space-time, where time is just another dimension like space. In this view, nothing happens. Everything just is. You're not moving through time. You're just a static four-dimensional object stretched from birth to death, and your consciousness is somehow moving along that static shape, creating the illusion of time passing. The paradox. This seems to eliminate free will. If the future already exists, can you actually make choices? Or are you just experiencing a predetermined path? It's philosophy meets physics, and there's no easy answer. Sleep tight. Okay. Now, Paradox 8, the time travel information paradox. Here's a fun variation on the bootstrap paradox. Imagine you build a computer that can send information back in time. Just data, not objects. You use it to send yourself the solution to an incredibly difficult math problem. You receive the solution, verify it works, and then send it back to yourself. Where did the solution come from? You didn't solve it. You just received it and passed it along. The information exists in a closed loop with no origin. But here's where it gets even weirder. What if you receive a message from your future self with information you haven't learned yet? Some versions of this paradox suggest that the universe might censor such information loops. Maybe quantum uncertainty makes it impossible to send precise information backward. Or maybe the information degrades each loop until it becomes noise. Others argue it could work fine, but it would create bizarre situations where knowledge has no source. Imagine receiving the cure for cancer from your future self, who received it from their future self, in an endless loop. Should we take it? Can we trust information that was never discovered, only circulated? Questions for another time, or is it the same time? Who knows? Now, Paradox 9, Novikov Self-Consistency Principle Paradox. Russian physicist Igor Novikov proposed a solution to time travel paradoxes that's both reassuring and kind of creepy. He suggested that the universe enforces self-consistency. In other words, if time travel to the past is possible, you can only do things that were always part of history. You can't change the past because anything you do in the past already happened. Sounds good, right? No paradoxes! But here's where it gets weird. This means the universe somehow conspires to stop you from creating paradoxes. If you try to shoot your grandfather, the gun jams. If you try to warn people about a disaster, they don't believe you. If you try to change anything, improbable coincidences prevent you. The paradox is this: who or what is enforcing consistency? Is the universe itself conscious? Does probability warp itself around your actions? And what about free will? If you literally cannot make choices that would change the past, are you really free? It's a solution that trades one mystery for another. You get rid of logical paradoxes, but you introduce a universe that seems to be actively managing timeline coherence. That might be even weirder than paradoxes themselves. The universe becomes a cosmic editor, and you can't break the plot. Now time for Paradox 10, the arrow of time paradox. Why does time only go forward? Seriously, think about it. The fundamental laws of physics, Newton's laws, quantum mechanics, even relativity, they almost all work the same whether time runs forward or backward. You could film particles colliding, play it backward, and the physics would still check out. So why do we only experience time in one direction? Why do we remember the past but not the future? Why do eggs scramble but never unscramble? Why does entropy disorder always increase? This is the arrow of time paradox. The usual answer involves thermodynamics and the second law. Entropy increases over time. But that just pushes the question back. Why did the universe start in a low entropy state at the Big Bang? That initial condition seems incredibly unlikely, almost like the universe was carefully set up to have a direction to time. And here's the kicker. If the universe eventually reaches maximum entropy, heat death, does the arrow of time disappear? Does time lose its direction when there's no change left to happen? Some physicists think time itself might be an emergent property, not fundamental. Maybe time is just something that happens when entropy exists, and that's beautifully strange. Let's end this segment with one of the deepest time paradoxes in physics: closed time-like curves, or CTCs. These are paths through space-time that loop back on themselves, meaning if you follow one, you end up in your own past. General relativity allows them to exist under certain conditions, like near-rotating black holes or with exotic matter. But if CTCs exist, you get all the paradoxes we've talked about: grandfather problems, bootstrap loops, information without origin. Most physicists assume something in the universe prevents CTCs from actually forming. Maybe quantum mechanics steps in, or maybe you need exotic matter that can't exist. But here's the problem. We don't have a fundamental law that forbids them. It's more like a strong suspicion. Some researchers even study CTC physics, asking what the rules would be if they existed. One idea: timelines would have to be consistent, like Novikov suggested, meaning only self-consistent loops are allowed. The paradox is that our best theory of gravity says time travel is possible, but our intuition and logic scream that it can't be. Either general relativity is incomplete, or the universe is far stranger than we think. And honestly, both options are kind of exciting. And that wraps up our journey through time and causality paradoxes. 11 brain-bending problems that show just how strange time really is. But we're just getting started. Up next, we're going to stretch your mind in a different direction. Literally. Let's talk about infinity and all the impossible things that come with it. All right, we've bent time into pretzels. Now let's talk about something equally mind-melting. Infinity. And not just infinity as this abstract concept, but infinity as it shows up in the actual universe. Because here's the thing about infinity. Our brains didn't evolve to handle it. We're built for counting sheep and berries, not for wrapping our heads around endless space or infinitely divisible distances. But the universe doesn't care what our brains can handle. It's possibly infinite, it's definitely weird, and when you start doing math with infinity, things get wonderfully broken. So let's explore 11 paradoxes that show just how strange infinity gets when it collides with reality. Get cozy, because we're about to zoom out really, really far. Here's a question that bothered astronomers for centuries. If the universe is infinite and filled with stars, why is the night sky dark? Think about it. If space goes on forever in all directions and it's packed with stars, then every single direction you look should eventually hit a star. The whole sky should be blazing bright, like looking at the surface of the sun from every angle. But it's not. It's mostly dark, with little points of light. This is Olber's paradox, named after the German astronomer who popularized it. For a long time, nobody had a good answer. Some thought maybe dust was blocking distant starlight. But dust would heat up and glow too. The real answer came from understanding that the universe isn't infinitely old and static. It had a beginning, the Big Bang, and it's expanding. Light from distant stars hasn't had time to reach us yet, and the expansion of space stretches light into wavelengths we can't see. So the dark night sky is actually evidence that the universe has a finite age and is changing. Darkness, it turns out, tells us something profound about cosmic history. Pretty cool that something as simple as a dark sky was a paradox that stumped brilliant minds for generations. Let's go way back to ancient Greece. A philosopher named Zeno came up with a series of paradoxes. And one of them goes like this. Imagine you want to travel from Earth to a star 1 light year away. First, you have to get halfway there. Then you have to cover half the remaining distance. Then half of what's left after that. Then half again. And again. And again. Since you can always divide the remaining distance in half, you have to complete an infinite number of steps. And how can you complete an infinite number of anything? Zeno argued that motion itself is impossible. It's an illusion. Obviously, we know motion is real, but the paradox still bugs mathematicians and physicists. The resolution involves understanding infinite series. You can add up infinitely many numbers and get a finite result. Half plus a quarter plus an eighth and so on forever equals exactly 1. Calculus was basically invented to deal with problems like this. But here's what's wild. We still don't know if space and time are infinitely divisible or if there's a smallest possible unit, like the Planck length. If space is truly continuous, then Zeno was kind of right. Every journey involves infinite steps. We just happen to be able to complete them. And if space is quantized, made of discrete chunks, then infinity doesn't enter the picture the same way. Either way, getting from here to there is weirder than it seems. Here's a big one. Is the universe infinite or finite? Honest answer, we don't know. It could go on forever in all directions, or it could wrap back on itself like the surface of a sphere. Current observations suggest it's at least really, really big, bigger than the observable universe, which is already incomprehensibly huge. But here's the paradox. If the universe is truly infinite and matter is distributed roughly evenly, then everything that can happen does happen, somewhere. Not just once, infinitely many times. There are infinitely many copies of Earth. Infinitely many copies of you. Infinitely many versions where you made different choices. In fact, there are infinitely many identical copies of you reading this exact script at this exact moment. And infinitely many slightly different versions. This isn't speculation or multiverse theory. This is just a straightforward consequence of infinite space plus probability. If there's even a tiny chance of a particular arrangement of atoms, and you have infinite space to play with, that arrangement occurs infinitely often. It's called the infinite universe paradox, and it makes questions about identity really strange. Which one is the real you? Are you all equally real? Do your choices matter if infinite other yous are making every possible choice? It's dizzying. Infinity doesn't just mean really big. It means every possibility becomes a certainty, repeated endlessly. Okay, this one's a classic thought experiment. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on forever. Every room is occupied. The hotel is completely full. Now a new guest shows up. Normally you'd say, sorry, we're full. But the manager says no problem. He asks every guest to move to the next room. Guest in room 1 moves to room 2. Guest in room 2 moves to room 3, and so on. Now room 1 is empty, and the new guest checks in. The hotel was full, but it accommodated someone new. Weird, but okay. Now imagine an infinitely large bus pulls up with infinitely many new guests. Can the hotel fit them? Yep. The manager asks every current guest to move to the room number that's double their current room. Guest in room 1 goes to room 2, guest in room 2 goes to room 4, guest in room 3 goes to room 6. Now all the odd-numbered rooms are empty, and there are infinitely many of those. The infinite bus guests fill those rooms. This is Hilbert's Hotel, and it shows how infinity breaks our normal intuition. Infinity plus 1 equals infinity. Infinity plus infinity equals infinity. You can't fill it up. And here's the space connection. If the universe is infinite, it's kind of like Hilbert's Hotel. There's always room for more. Infinite space doesn't get used up. It's endlessly accommodating, which is both comforting and completely baffling. This next one is so counterintuitive that when it was first proven, people thought it was a joke. The Banach-Tarski paradox says you can take a solid sphere, like a ball, break it into a few pieces, and reassemble those pieces into two spheres identical to the original. You're doubling the ball, not by stretching or adding material, just by rearranging. One ball becomes two, same size, same everything. How? It relies on infinity and the weirdness of mathematical sets. The pieces you break the ball into aren't normal pieces. They're infinitely complex, scattered sets of points that don't have well-defined volumes. You can't actually do this with a physical ball because matter is made of atoms, and you'd need to break it into pieces that are weirder than anything physical. But mathematically it works. The paradox shows that our intuitive idea of volume breaks down when infinity is involved. You can create something from nothing, in a sense, just by exploiting infinite divisibility. Some physicists wonder if something like this could apply in the real universe. Could you duplicate matter using the strange properties of space at quantum scales? Probably not, but the fact that the math allows it at all is unsettling. It suggests that infinity is not just big, it's reality-breaking in ways we don't fully understand. Here's a question. Can you complete an infinite number of tasks in a finite amount of time? It sounds ridiculous, but think about it this way. You perform one task in 30 seconds, then another task in 15 seconds, then another in 7.5 seconds. Each task takes half the time of the previous one. After 1 minute, you've done infinitely many tasks. This is called a supertask, and it's been debated by philosophers and mathematicians for decades. The problem is figuring out what state things are in after the supertask completes. Imagine a lamp that you turn on and off. You flip it on, then off, then on, then off, each time twice as fast as before. After 1 minute, you flip the switch infinitely many times. Is the lamp on or off? There's no answer. The sequence doesn't converge to a final state. It's undefined. Some people say this proves supertasks are impossible. They lead to contradictions, so they can't happen in reality. Others say they're possible in principle, but show how infinity creates ambiguity. In relativity, you can actually experience something like a supertask if you fall into a black hole. An outside observer sees you slow down and take infinite time to cross the event horizon. But from your perspective, you cross in finite time. The universe is packed with situations where infinity and finite quantities clash, and supertasks are one of the cleanest examples. They're impossible and possible at the same time, depending on how you look at them. Here's a shape that will mess with you. Imagine a horn, like a trumpet, that extends infinitely in one direction, getting narrower and narrower but never quite closing. This is Gabriel's horn, a mathematical object you can create by rotating a simple curve around an axis. Here's the paradox. The horn has finite volume but infinite surface area. You could fill it with a finite amount of paint, but you'd need an infinite amount of paint to cover its surface. Wait, what? If you fill it with paint, doesn't that cover the inside surface? The paradox is a quirky result of how volume and surface area scale differently as the horn narrows. The volume converges to a finite number, but the surface area just keeps adding up, never stopping. It's mathematically rigorous and completely weird. Some people use this as an argument that infinity leads to nonsense. How can something hold finite paint but need infinite paint to coat? Others say it's just a reminder that our physical intuitions fail at infinity. In space, you could imagine structures with similar properties, like infinitely long cosmic strings or fractal-shaped clouds. The paradox shows that infinity doesn't just mean keeps going. It means the rules change. Volume and surface don't have to relate the way we expect. Gabriel's horn is beautiful, paradoxical, and a perfect example of how math can describe things that feel impossible. You probably think infinity is infinity, right? Just one thing. Endless. Nope. There are different sizes of infinity, and some infinities are literally bigger than others. This is Cantor's infinity paradox, discovered by mathematician Georg Cantor in the late 1800s. He proved that the set of all whole numbers, 1, 2, 3, and so on, is infinite. But the set of all real numbers, which includes decimals and irrational numbers, is a bigger infinity. You can't match them up one to one. No matter how you try, there are always more real numbers left over. There's no largest infinity either. You can always construct a bigger one. Cantor's work was so controversial that some mathematicians rejected it, and it reportedly drove him to psychological breakdowns. But it's been confirmed and expanded. Modern math relies on different levels of infinity. Here's the space connection. If the universe is infinite, which kind of infinity is it? Are there infinitely many particles or infinitely many points in space, or both? And are those different sizes of infinity? Can the universe contain all possible infinities, or only some? Cantor's paradox suggests that infinity isn't just one concept. It's an endless hierarchy of endlessness. And that's somehow more infinite than infinity, which is just wild. The universe might not just be infinite. It might be infinite in ways we can't even count. Here's a geographic paradox that applies to the cosmos. If you try to measure the coastline of an island, you get different answers depending on your ruler. Use a mile-long ruler, you get one number. Use a foot-long ruler and follow the curves more closely, the coastline gets longer. Use an inch-long ruler, longer still. In fact, the more precisely you measure, the longer the coastline becomes. If you measure every tiny pebble and grain of sand, the coastline approaches infinite length. This is the coastline paradox, and it reveals something deep about fractals, shapes that have detail at every scale. The universe might be fractal-like in structure. When we map galaxies, we see clusters, then superclusters, then filaments and voids, and the pattern seems to repeat at different scales. If the universe has fractal geometry, then questions about its size and shape get really strange. How do you measure the distance between 2 points if space itself is wrinkly at every scale? Does a straight line even exist, or is every path infinitely long when you zoom in? Some theories suggest space-time itself might be fractal at the quantum level, foamy and turbulent when you look closely enough. The coastline paradox is a reminder that measurement depends on perspective. There might not be one true answer to how big is the universe. It might depend on what scale you're asking from, and that's beautifully, frustratingly paradoxical. This one's more playful, but still thought-provoking. Most numbers are pretty boring, right? Like 8,412,903. Nothing special about that number. But some numbers are interesting, like 0, first whole number, the concept of nothing, or pi, ratio of a circle's circumference to its diameter, irrational and infinite. Or Graham's number, so huge it can't be written down. Now here's the paradox. Suppose there exists a set of uninteresting numbers. Okay, so take the smallest uninteresting number. But wait, being the smallest uninteresting number is a pretty interesting property. So it's not uninteresting after all. Remove it from the set. Now there's a new smallest uninteresting number, which is also interesting for the same reason. You can keep doing this forever. Conclusion: all numbers are interesting. But that can't be right. Most numbers are clearly boring. This is the interesting number paradox. And while it's a bit tongue-in-cheek, it touches on real issues in logic and set theory. It's similar to paradoxes about definability and self-reference. In cosmology, you could ask a similar question. Are there boring regions of an infinite universe? Or is every region interesting in some way, even if it's just for being the most boring? If the universe is infinite, does that mean it contains every possible interesting structure, making even the boring parts interesting by context? It's a silly paradox with surprisingly deep roots. Last one for this segment, and it's delightfully strange. Imagine you have an infinitely large vase and an infinite collection of balls, numbered 1, 2, 3, and so on. At 1 minute before noon, you put balls 1 through 10 into the vase and remove ball number 1. At 30 seconds before noon, you add balls 11 through 20 and remove ball 2. At 15 seconds before noon, you add 10 more and remove ball 3. You keep going, each step taking half as long as the previous. You're always adding 10 balls and removing 1, so the vase should be getting fuller, right? But here's the paradox. At exactly noon, the vase is empty. Why? Because every ball has a number, and at some point before noon, you removed that specific ball. Ball 1 was removed in the first step, ball 2 in the second step, ball 100 in the 100th step. Every numbered ball gets removed. So even though you added infinitely many balls and it seems like the vase should have infinitely many balls left, it's actually empty. This is the Ross-Littlewood paradox, and it shows how infinity can defy our intuition about accumulation. You can do infinitely many actions that seem to be adding up, but end with nothing. It's related to supertasks and questions about what happens at the limit of an infinite process. Some argue this proves supertasks are incoherent. Others say it just shows you have to be careful about infinity. Either way, it's a perfect example of how infinity doesn't play by normal rules. And that's our tour through infinity and scale paradoxes. 11 mind-bending examples of how the universe gets weird when things go on forever, or when you zoom in too close, or when you try to count the uncountable. But we're not done yet. Next up, we're diving into the quantum realm, where just looking at something changes it. Let's talk about observation and the deeply strange paradoxes that come from trying to measure reality. All right, time to get quantum. And I'm warning you right now, this segment is going to feel different from the last two. Because with time and infinity, things were weird, but at least they made a kind of sense. Quantum mechanics? Quantum mechanics doesn't care about making sense. It cares about being accurate. And it's the most accurate scientific theory we've ever created. Its predictions have been confirmed to absurd levels of precision. But the price we pay for that accuracy is that reality at the smallest scales is absolutely bonkers. Particles exist in multiple states at once. Measuring something changes it. Things on opposite sides of the universe affect each other instantly. And the act of observation, just looking, seems to play a fundamental role in how reality works. So let's dive into 11 quantum paradoxes that'll make you question whether the universe is really there when nobody's watching. Settle in, because things are about to get wonderfully uncertain. Let's start with probably the most famous thought experiment in all of quantum physics. You've got a cat in a sealed box. Inside the box is a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the Geiger counter detects it, triggers the hammer, breaks the vial, and the cat dies. If the atom doesn't decay, the cat lives. Simple enough. But here's where quantum mechanics comes in. That radioactive atom exists in a superposition. It's both decayed and not decayed at the same time until someone measures it. And according to the math, that means the entire system is in superposition. The cat is both alive and dead simultaneously until you open the box and observe it. Schrödinger came up with this to show how absurd quantum mechanics seemed when applied to everyday objects. It was supposed to be a criticism, but the math doesn't care. As far as quantum mechanics is concerned, the cat really is in both states. Now take this to space. Is the moon there when nobody's looking at it? Einstein asked this seriously. If observation collapses quantum states, what counts as an observer? Does a rock count? Does a camera? Or does it require consciousness? Some interpretations say the universe itself exists in superposition until observed. Other interpretations say everything is always real, we just can't see all the branches. Either way, Schrödinger's cat is still messing with our heads a century later, and we still don't have a universally accepted answer. Sweet dreams. Here's a quantum effect that sounds like magic. If you keep observing a quantum system, you can prevent it from changing. It's called the quantum Zeno effect, named after our old friend Zeno and his paradoxes. Here's how it works. Imagine you have an unstable particle that should decay within a second. Normally, it has a certain probability of decaying at any given moment. But if you measure whether it's decayed or not multiple times per second, the act of measurement keeps resetting the quantum state. The particle never gets a chance to decay. You freeze it in place just by watching it. This has been experimentally confirmed. Observation literally prevents change. Now here's the paradox. What counts as an observation? Does the particle know it's being watched? Does the universe keep track of what's measured and what isn't? And here's the space version. Could you prevent stars from dying by observing them? Obviously not with human eyes, but what if there's some cosmic observation happening constantly? Some interpretations of quantum mechanics suggest the universe is always observing itself through interactions. Others say consciousness is required. The quantum Zeno effect shows that observation isn't passive, it's active. It does something. And we still don't fully understand what. The universe changes when watched. That should bother you, and it definitely bothered Einstein. Einstein hated quantum mechanics. Not because it didn't work, he knew it worked, but because it seemed incomplete. So in 1935, he and two colleagues, Podolsky and Rosen, came up with a thought experiment designed to show quantum mechanics was missing something. Here's the setup. You create two particles that are entangled, linked in such a way that their properties are correlated. You send one particle to one side of the galaxy and one to the other. Light years apart. Now you measure one particle, say its spin, and you instantly know the spin of the other particle. But here's the thing. Before you measured, neither particle had a definite spin. They were both in superposition. So how did the second particle know what state to be in the moment you measured the first? Einstein called this spooky action at a distance and argued it proved quantum mechanics was incomplete. There must be hidden information, hidden variables, that determine the outcome in advance. But decades later, a physicist named John Bell came up with a test, and experiments have confirmed it over and over. There are no hidden variables. The particles really don't have definite properties until measured. And measuring one really does instantly affect the other, no matter the distance. It's not sending information faster than light because you can't control the outcome, but the correlation is real and instant. Entanglement is real. The universe is non-local. And that's deeply, deeply weird. Space doesn't separate everything the way we think it does. This one will twist your brain. Imagine you send a photon, a particle of light, toward a half-silvered mirror that either reflects it or lets it pass through. You set up detectors on both paths. Classically, the photon either goes one way or the other. But quantum mechanically, it goes both ways at once, in superposition, until you measure it. Okay, weird, but we've covered that. Now here's the twist. After the photon has already passed the mirror, after it's committed to a path, so to speak, you randomly decide whether to recombine the paths or keep them separate. If you recombine them, the photon shows interference, meaning it must have traveled both paths. If you keep them separate, it shows up in one detector or the other, as if it only took one path. So you're making a choice after the photon already made its choice, and somehow your future decision affects its past behavior. This is Wheeler's delayed choice paradox. And experiments confirm it. You can even do it with photons from distant stars, photons that have been traveling for millions of years. Your choice today about how to measure them seems to reach back in time and determine which path they took millions of years ago. The resolution, according to quantum mechanics, is that the photon doesn't take a definite path until measured. The past isn't fixed until observed. But that's almost more disturbing than the paradox. It suggests history is flexible, determined retroactively by observation. The universe's past might be created by its present. Think about that. Here's the big one, the foundational problem that every interpretation of quantum mechanics has to deal with. When you're not looking, quantum systems exist in superposition, multiple states at once, described by a wave function. But when you measure them, the wave function collapses, and you get one definite outcome. Why? What counts as a measurement? What causes the collapse? This is the measurement problem, and nobody has a universally accepted answer. Some say consciousness causes collapse. The act of a mind observing reality forces it to pick a state, but that seems to give humans magical powers. Others say decoherence. Interaction with the environment causes collapse, but that just pushes the question back. When does environment count? The many worlds interpretation says there's no collapse at all. Every outcome happens, splitting the universe into branches. You just experience one branch. Copenhagen interpretation says the wave function is just information, and collapse is updating your knowledge. But that feels like dodging the question. Here's why it matters for space. The cosmic microwave background radiation we see from the Big Bang, has it been measured, or is it still in superposition? If a photon from the edge of the universe travels 13 billion years and nobody ever observes it, did it have a definite path? The measurement problem isn't just academic. It's about what's real and when reality happens. And after a century of quantum mechanics, we still don't know. Okay, this one builds on the measurement problem and makes it even worse. Imagine you're doing a quantum experiment in a sealed lab. You measure a particle, and the wave function collapses. You see a definite result. But your friend is outside the lab, isolated from the experiment. From their perspective, you and the particle and the lab are all one big quantum system, still in superposition. You haven't experienced a collapse. You're in a superposition of having seen different results. So who's right? Did the wave function collapse or not? This is Wigner's friend paradox, named after physicist Eugene Wigner. It's like Schrödinger's cat, but instead of a cat, it's a conscious observer. You're both alive and dead, so to speak. You've seen different results in different branches. Your friend outside could, in principle, do an interference experiment on the whole lab to prove you're still in superposition. But from your perspective, inside the lab, you saw one outcome. Both perspectives are valid according to quantum mechanics. Recent variations of this experiment have been done with photons playing the role of observer, and they confirm the paradox. There's no universal wave function collapse. Reality is observer-dependent, not just unknown, actually different depending on who's looking. Some physicists think this proves many worlds is right. Others think it shows we need a new theory. But the paradox is real, experimentally verified, and it means objective reality might not exist the way we thought. What you see and what I see might genuinely be different, both real, both valid. This one is just beautiful and mind-bending. You do a version of the double-slit experiment where you mark which path a photon takes. When you mark the path, the photon behaves like a particle, no interference pattern. When you don't mark it, it behaves like a wave. You see interference. Makes sense so far, but here's the quantum eraser twist. After the photon has already hit the detector screen, You can choose whether or not to erase the which path information. If you erase it, the interference pattern appears. If you don't erase it, no interference. So your decision after the photon has already been detected seems to retroactively change whether it behaved like a wave or particle during the experiment. You're erasing information in the future, and it changes the past. Experiments confirm this works. The resolution is that you're not actually changing the past. You're changing which subset of data shows the pattern. The interference is always there in the correlations, but you only see it when you erase the path information. But that explanation doesn't make it less weird. It means information and observation have this deep, non-intuitive relationship with physical outcomes. Quantum mechanics doesn't just say, we can't know everything. It says that what we choose to know changes what happened. The act of seeking information alters the history of the system. The universe is interactive in a way that feels almost conversational. You ask a question, reality answers, but the answer depends on the question. You've probably heard of Heisenberg's uncertainty principle. You can't simultaneously know both the exact position and exact momentum of a particle. The more precisely you measure one, the less precisely you know the other. But this isn't about measurement tools being imperfect. It's fundamental to reality. The particle doesn't have a definite position and momentum at the same time. It's not that we can't know, it's that they don't both exist as definite values. Here's the paradox version. If a particle doesn't have a definite position, where is it? If it doesn't have definite momentum, how fast is it moving? The answer is it exists in a spread of possibilities. It's not at one point, it's smeared out. Not because it's moving, but because location itself is fuzzy. Apply this to the universe. Every particle in your body is slightly uncertain in position. You're a cloud of probability. And here's the kicker. Uncertainty applies to energy and time too. A particle can borrow energy from nothing, as long as it pays it back quickly enough that the universe doesn't notice. Virtual particles pop into existence constantly, everywhere because of this. The vacuum of space isn't empty. It's seething with particles flickering in and out of existence. The uncertainty principle means reality is never still, never certain, never definite. The universe, at its smallest scale, is a blur, and that blur is holding everything together. Quantum uncertainty isn't a bug. It's a feature. Without it, atoms wouldn't be stable. Matter wouldn't exist. You wouldn't exist. The paradox is that definite reality emerges from fundamental indefiniteness. This is the experiment that started it all. You shoot particles, electrons, photons, whatever, at a barrier with two slits. On the other side, you have a detector screen. If you cover one slit, particles pile up in one spot, like bullets. Makes sense. But if you open both slits, you don't get two piles. You get an interference pattern, alternating bright and dark bands. That only happens with waves. Water waves, sound waves, light waves. They interfere with each other. But particles aren't waves, or are they? Here's where it gets truly weird. You can shoot particles one at a time. Single electrons, with minutes between them. Each one hits the screen at one point, like a particle. But over time, the pattern that builds up is an interference pattern. Each particle somehow went through both slits and interfered with itself. But if you put a detector at the slits to see which one the particle goes through, the interference pattern disappears. Just by checking, you change the outcome. The particle stops acting like a wave and acts like a particle. Observation changes reality. This experiment has been done thousands of times with particles of increasing size. It always works the same way. Matter is both wave and particle, and which one you see depends on what you're looking for. The double-slit experiment is quantum mechanics in its purest, most undeniable form. And it makes no intuitive sense. We just have to accept that reality is weirder than our brains evolved to comprehend. So particles are sometimes waves and sometimes particles. But what does that actually mean? Are they tiny solid balls or spread out ripples, or what? The answer, maddeningly, is both and neither. Wave-particle duality is the idea that quantum objects don't fit into classical categories. They have properties of both, depending on context. A photon is a wave when it travels, spreading out, diffracting, interfering. But it's a particle when it interacts, hitting a detector at a single point, carrying discrete energy. Electrons orbit atoms like clouds, not like little planets. But when you detect one, you find it at a point. Here's the paradox. How can something be two contradictory things? It feels like saying a thing is both a rock and a river. The resolution is that waves and particles are both incomplete human metaphors. The real thing is a quantum object, described by math, and we just use whichever classical analogy is convenient at the time. But that's unsatisfying. We want to know what it really is. And quantum mechanics says that's the wrong question. There is no deeper reality beneath the wave function. The wave function is reality. Or maybe reality doesn't exist until measured. Or maybe reality splits every time there's a choice. Depending on your interpretation, you get different answers. But they all agree on this. The universe at its fundamental level doesn't match our experience. We live in a classical world built on quantum foundations. And the gap between the two is the wave-particle duality paradox. We experience one kind of reality, but it's made of something completely different. Last one for this segment, and it's dark but fascinating. Imagine you're about to do something dangerous. Let's say a quantum experiment with a 50-50 chance of killing you. But here's the quantum twist. At the moment of the experiment, the universe splits into two branches. In one branch, you die. In the other, you survive. From the perspective of the dead you, the story's over. But from the perspective of the surviving you, you always experience the branch where you survived. So you do the experiment again. 50-50 odds, you survive again, and again, and again. From your subjective experience, you're immortal. No matter how many times you do the experiment, you always find yourself in the branch where you lived. This is quantum immortality, an idea that comes out of the many worlds interpretation. Here's the paradox. If many worlds is true, then from your subjective viewpoint, you can never experience dying. You'll always find yourself alive, even if the odds get astronomically small. You'll live forever in your own timeline, watching everyone around you age and die, while you inexplicably survive every danger. Of course, from everyone else's perspective, you died ages ago in most branches. Only a few rare branches contain ancient, improbable you. Most physicists think this is more philosophy than physics, and there's no way to test it since the dead versions can't report back. But it raises real questions about identity and probability in a quantum multiverse. If every outcome happens, which one are you? All of them? Or just the one you experience? And if you only experience one, why that one? Quantum immortality won't help you live forever in anyone else's story, but maybe, just maybe, you live forever in your own. And that's our journey through observation and quantum paradoxes. 11 examples of how reality gets slippery when you look at it too closely. Measurement changes things. Observation creates outcomes. The universe seems to play by different rules depending on whether anyone's watching. But we're far from done. Up next, we're zooming back out to the biggest scales imaginable. Let's talk about cosmology, the universe as a whole, and the paradoxes that emerge when you try to understand everything at once. We've traveled through time, wrestled with infinity, and watched reality dissolve under observation. Now it's time to zoom all the way out and look at the universe itself. Not just parts of it, not just how it works locally, but the whole thing, the cosmos. Everything that exists, all at once. And when you do that, when you try to understand the universe as a single object with a history and a fate, you run into paradoxes that are absolutely massive in scale. These aren't thought experiments about cats in boxes. These are real observational mysteries that cosmologists are actively trying to solve. Why is the universe the way it is? Why does it seem fine-tuned for life? Where is everybody? These 11 paradoxes live at the intersection of observation and theory, where what we see doesn't quite match what we expect. So let's expand our view to the cosmic scale and see what breaks. Let's kick things off with maybe the most famous paradox in all of cosmology. It's called the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a lunch conversation, "Where is everybody?" Here's the problem. Our galaxy contains hundreds of billions of stars. Many of those stars have planets. The universe is almost 14 billion years old. Even if intelligent life is rare, and even if space travel is slow, a single civilization could colonize the entire galaxy in just a few million years using self-replicating probes. That's nothing on cosmic timescales. So if life is remotely common, the galaxy should be teeming with civilizations. We should see evidence everywhere. Megastructures, radio signals, probes, something. But we see nothing. Silence. We appear to be completely alone. So where is everybody? Maybe life is incredibly rare. Maybe intelligence is a dead end, and civilizations destroy themselves. Maybe they're here but hiding. Maybe we're the first. Or maybe advanced civilizations transcend physical form and we wouldn't recognize them. Every answer raises new questions. The Fermi paradox isn't just about aliens. It's about our place in the universe. Are we special, alone, early, or just not looking in the right way? The silence is deafening, and we don't know what it means. Now let's talk about something called the flatness problem. When cosmologists measure the geometry of the universe, they find that it's remarkably flat. Not flat like a pancake, but flat in the sense that parallel lines stay parallel. The angles of a triangle add up to 180 degrees, the kind of geometry you learned in school. The universe could have been curved, positively or negatively, but it's not. It's flat to an incredible degree of precision. Here's why that's a problem. In the early universe, right after the Big Bang, even a tiny deviation from perfect flatness would have been amplified enormously as the universe expanded. If the universe was even slightly curved back then, it should be wildly curved now, either collapsing back on itself or expanding so fast that matter could never clump together. But it's not. It's just right. For the universe to be this flat today, it had to be tuned to flatness in the early moments to an absurd precision. 1 part in 10 to the 60th or something ridiculous. That level of fine-tuning seems impossibly unlikely unless something set it that way. The leading explanation is cosmic inflation, a period of exponential expansion right after the Big Bang that stretched the universe so fast it ironed out any curvature. Inflation works mathematically and solves the flatness problem, but it raises its own questions. What caused inflation? Why did it stop? The flatness problem shows that the universe looks designed to be just right, even though nobody designed it. That brings us to another cosmic head-scratcher known as the horizon problem. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it's incredibly uniform. The temperature is the same in every direction to within 1 part in 100,000. That's weird because different parts of the sky are so far apart that light hasn't had time to travel between them since the Big Bang. They're beyond each other's horizons. They've never been in contact. So how did they end up at the same temperature? It's like finding 2 isolated islands with identical ecosystems even though they've never exchanged species. In normal cosmology, there's no reason for distant parts of the universe to be the same. They couldn't have influenced each other. But they are the same. Again, cosmic inflation is the standard answer. If the universe went through a period of faster-than-light expansion, regions that are now far apart were once close together in thermal contact and then got stretched to cosmic distances. That explains the uniformity. But without inflation, the horizon problem is deeply mysterious. Why is the universe so smooth and homogeneous when it had no time to smooth itself out? It suggests something happened in the first tiny fraction of a second that set the initial conditions very carefully. Here's a really strange one that sounds like science fiction but is taken seriously by physicists. It's called the Boltzmann brane paradox. Ludwig Boltzmann was a physicist who worked on thermodynamics and entropy. The paradox goes like this. If the universe is eternal or very, very long-lived, and if quantum fluctuations can randomly produce anything given enough time, then it's more likely for a single conscious brain to randomly pop into existence, complete with false memories, than for an entire universe with a consistent history to exist. Think about it. A brain is way simpler than a whole universe. Random fluctuations in a void would produce lone brains far more often than they'd produce galaxies and stars and planets with real histories. So statistically, if you're a conscious observer, you're more likely to be a Boltzmann brain, a spontaneous fluctuation that will dissolve back into chaos in a moment, than a real person in a real universe. Your memories are fake. Everything you perceive is hallucination. You'll cease to exist in seconds. Obviously, we don't think that's true, but the paradox is that some cosmological models predict Boltzmann brains should vastly outnumber real observers. If your theory predicts you're probably a random fluctuation, your theory is probably wrong. This paradox is used to rule out certain models of eternal universes. It shows that getting the statistics of observers right is harder than it sounds. Let's shift to something a bit more poetic but equally troubling, the heat-death paradox. The second law of thermodynamics says entropy always increases in a closed system. Disorder grows, energy spreads out, and the universe is a closed system. So eventually, in the far, far future, all the stars will burn out, all the black holes will evaporate, and all matter and energy will be spread uniformly through an ever-expanding void. Maximum entropy. No gradients, no energy flow, no structure. This is called heat death, and it seems to be the ultimate fate of the universe. But here's the paradox. If the universe is headed toward maximum entropy, why is it so far from maximum entropy now? Why did it start in such a low entropy state? The Big Bang was incredibly organized, all matter and energy concentrated in a tiny space. That's the opposite of maximum entropy. It's like finding a pristine, organized room and being told it's going to slowly get messy. Okay, fine, but why was it clean to start with? The initial low entropy of the universe is one of the biggest unsolved problems in cosmology. Some think it's just a lucky accident. Some think inflation explains it. Some think time itself emerges from entropy gradients, and asking what came before low entropy is meaningless. Either way, the universe seems to have started in an incredibly special state, and we don't know why. Heat death is our future, but our past is just as mysterious. Speaking of the Big Bang, let's talk about the Big Bang singularity paradox. According to general relativity, if you run the expansion of the universe backward in time, everything converges to a single point of infinite density and temperature. A singularity. The math breaks down. Density becomes infinite, space-time curvature becomes infinite, and our equations literally give nonsense answers. Physics stops working. But that singularity is supposed to be the beginning of the universe. So the paradox is that our best theory of cosmology predicts its own failure at the most important moment, the origin of everything. We can describe the universe from a tiny fraction of a second after the Big Bang, but not at the Big Bang itself. Some physicists think quantum mechanics will fix this, that there's no true singularity once you account for quantum gravity. Others think time itself doesn't exist at the singularity, so there's no moment of creation to explain. String theory, loop quantum gravity, and other approaches try to resolve this, but we don't have experimental data from those conditions. The Big Bang singularity paradox is a sign that we're missing something fundamental. Our physics has a blind spot at the very beginning of time, and until we fix that, the ultimate origin of the universe remains paradoxical. This next one is a real puzzle for physicists, and it's called the cosmological constant problem. Einstein's equations allow for a term called the cosmological constant, which represents the energy of empty space itself, vacuum energy. When physicists try to calculate what this value should be based on quantum mechanics, they get a number that's about 10 to the power of 120 times bigger than what we actually observe. That's not a little bit wrong. That's the worst prediction in the history of physics. If the vacuum energy were really that large, the universe would have blown apart instantly. Matter could never have formed. We wouldn't exist. But we do exist, so the vacuum energy must be much, much smaller. In fact, observations show it's not zero. There's a small cosmological constant that's causing the expansion of the universe to accelerate, which we call dark energy. But why is it so small? Why is it just the right value to allow galaxies and stars and life, instead of being the huge value that quantum theory predicts? This is the cosmological constant problem, and it's one of the deepest mysteries in fundamental physics. Some think it's anthropic. We observe a small value because only in universes with small values can observers exist. Others think there's a symmetry or mechanism we don't understand that cancels out the vacuum energy. But right now, it's a paradox. Theory and observation disagree by 120 orders of magnitude. All right, next up we have the missing antimatter paradox, and this one cuts to the heart of why we exist at all. According to physics, matter and antimatter should have been created in equal amounts during the Big Bang. When a matter particle and an antimatter particle meet, they annihilate into pure energy. So if the early universe had equal amounts, everything should have annihilated, leaving a universe filled with light but no matter. No atoms, no stars, no us. But we exist. The universe is made almost entirely of matter, with only tiny traces of antimatter. So where did all the antimatter go? Why is there an asymmetry? This is called baryon asymmetry, and it's one of the great unsolved problems. There must have been some process in the early universe that favored matter over antimatter, even slightly. One extra matter particle for every billion matter-antimatter pairs would be enough. Physicists have found some mechanisms that could create this imbalance, involving the weak nuclear force and certain particle decays. But the known mechanisms aren't strong enough to explain the amount of asymmetry we see. There's something missing. Some new physics we don't understand. The missing antimatter paradox is the reason you exist, and we don't fully know why. Let's dive into something a bit more obscure but equally fascinating, the lithium problem. When physicists model the first few minutes after the Big Bang, they can predict how much of each light element should have been created. Hydrogen, helium, lithium. The predictions for hydrogen and helium match observations beautifully. But lithium doesn't. We observe only about a third of the lithium-7 that Big Bang nucleosynthesis predicts should exist. It's missing. Now that might not sound like a big deal, but it's a real problem because the same model that correctly predicts hydrogen and helium fails for lithium. Either something destroyed lithium in stars more efficiently than we thought, or our model of the early universe is wrong, or there's new physics involved. Some think lithium was destroyed in the outer layers of old stars. Others think dark matter particles affected nucleosynthesis. Some think the fundamental constants were slightly different in the early universe. The lithium problem is small in scale, but big in implications. When your most successful cosmological model gets one prediction wrong, you have to take it seriously. Something about the first 3 minutes of the universe isn't quite right. Now here's a weird observational anomaly that cosmologists are still arguing about. It's called the axis of evil. And no, that's not dramatic naming. Well, okay, it's a little dramatic. When we map the cosmic microwave background, the radiation from the Big Bang, we expect it to be statistically random and isotropic, the same in all directions. And mostly it is. But there's a strange feature. Some of the large-scale patterns in the temperature fluctuations seem to be aligned with each other and with the plane of the solar system. That shouldn't happen. The cosmic microwave background comes from the entire observable universe, billions of light years away. It should have nothing to do with our tiny solar system. But the data shows this alignment. Some call it the axis of evil because it hints that maybe the universe has a preferred direction, which would break the cosmological principle that says the universe is the same everywhere. Most physicists think it's a coincidence or a subtle instrumental artifact. The statistics aren't quite strong enough to be definitive. But if it's real, it's deeply weird. Why would the largest structures in the universe align with our local neighborhood? Is it coincidence? A flaw in our analysis? Or a hint that the cosmological principle is wrong and the universe actually has structure on the largest scales that we don't understand? The axis of evil is probably nothing, but probably isn't the same as definitely. Let's wrap up this segment with a recent mystery that's still unfolding: the Edges signal paradox. A few years ago, a radio telescope called Edges detected an absorption signal in radio waves from the early universe, specifically from a period called the Cosmic Dawn when the first stars were forming. The signal was stronger than expected, much stronger. According to the data, the primordial hydrogen gas was colder than it should have been. That's weird, because we thought we understood the thermal history of the early universe pretty well. If the gas was colder, something must have cooled it. But what? One possibility is interactions with dark matter. Maybe dark matter particles were sapping energy from normal matter in the early universe. That would be huge, because we've never directly detected dark matter interactions before. Another possibility is that the signal is wrong, caused by interference or calibration issues. The result hasn't been independently confirmed yet, so a lot of physicists are skeptical. But if it's real, the Edge's signal paradox could be our first direct evidence of dark matter doing something other than just pulling on things with gravity. It could also mean our models of the early universe are incomplete. Either way, it's a reminder that the universe still has surprises. We think we've got the big picture figured out, and then an unexpected radio signal shows up and makes us question everything. And that wraps up our tour of cosmological and universal paradoxes. 11 mysteries that span the entire history and structure of the cosmos. Missing antimatter, fine-tuned flatness, the silence of empty space, and signals from the cosmic dawn. But we're not done with the universe yet. Next, we're going to talk about the most extreme objects in existence. Places where space-time breaks, where physics gets pushed to the absolute limit. Let's talk about black holes and the paradoxes that lurk at their edges. We've looked at the universe as a whole, and now it's time to focus on the most extreme, most violent, most reality-warping objects in that universe. Black holes. These aren't just heavy stars or dense objects, they're places where the normal rules completely break down, where space and time swap roles, where you can fall in but never climb out, where the very concept of information, entropy, and quantum mechanics slam into general relativity and create contradictions that physicists are still trying to resolve. Stephen Hawking spent decades working on black hole paradoxes. Einstein didn't believe they could exist. And even today, with observational evidence that they're real, we still don't fully understand what happens at their edges or in their cores. So let's descend into the darkness and explore 11 paradoxes that live in the most extreme conditions the universe has to offer. Brace yourself. Things are about to get heavy. Let's start with the biggest, most important black hole paradox of them all. It's called the information paradox, and it nearly broke theoretical physics. Here's the setup. In quantum mechanics, information is never destroyed. If you know the complete state of a system now, you can, in principle, calculate what it was in the past and what it will be in the future. Information is conserved, but black holes seem to violate this. When something falls into a black hole, it disappears beyond the event horizon. All the information about what fell in, every detail about the particles and their quantum states, seems to be lost forever. Then Stephen Hawking showed that black holes evaporate over time by emitting radiation. Eventually, the black hole disappears completely. So where did the information go? If it's destroyed, quantum mechanics is wrong. If it somehow escapes in the Hawking radiation, we don't know how, because the radiation seems to be random thermal noise with no information encoded in it. For decades, this was an unsolved paradox. Recent ideas suggest information might be encoded on the event horizon or released in subtle correlations in the radiation, but there's no consensus. The information paradox sits at the collision point between quantum mechanics and gravity, and resolving it probably requires a theory of quantum gravity we don't have yet. It's the paradox that keeps theoretical physicists up at night. Now let's talk about something even stranger that came from trying to solve the information paradox. It's called the firewall paradox, and it's relatively recent, proposed in 2012. Here's the idea. If information can't be destroyed, then it has to escape a black hole somehow. But Hawking radiation is entangled with particles inside the black hole. Quantum mechanics says a particle can only be maximally entangled with one other particle. So if the radiation is entangled with stuff inside, it can't also carry information about what fell in earlier. Something has to give. One radical solution is that there's no smooth event horizon. Instead, there's a firewall, a wall of incredibly high energy radiation right at the horizon that incinerates anything trying to cross. This solves the information problem, but creates a new one. General relativity says you shouldn't notice anything special when you cross an event horizon of until you're ripped apart at the atomic level. For small black holes, this happens outside the event horizon. You'd be shredded before you even crossed the point of no return. For supermassive black holes, the tidal forces at the horizon are gentler, and you'd cross without noticing, only getting spaghettified much later as you approach the singularity. Here's the paradox. According to general relativity, an infalling observer shouldn't experience anything special at the horizon. It's not a physical boundary, just a mathematical one. But spaghettification is a very physical, very violent process. And from the outside, you never quite reach the horizon. You appear to freeze and fade. So do you get spaghettified or not? When does it happen? Different observers see different things, and both are correct within their own reference frames. Spaghettification isn't a logical paradox like the others, but it highlights how black holes make even the question of what happens to you deeply frame-dependent and weird. Now we arrive at the core of the problem, literally. The singularity paradox. At the center of every black hole, according to general relativity, is a singularity. A point of infinite density where all the mass is compressed to zero volume. Infinite curvature, infinite gravity. The math breaks down completely. Our equations output infinity, which in physics is usually a sign that your theory has failed. But the singularity isn't just a mathematical abstraction. It seems to be a real prediction. When matter collapses past a certain point, nothing can stop it. It just keeps compressing forever. Here's the paradox. Physics doesn't do well with infinities. We don't think anything in the universe is truly infinite. So either singularities don't actually form and something we don't understand stops the collapse, or they do form and there really are points of infinite density where the laws of physics cease to apply. Most physicists believe quantum gravity will resolve this. At the Planck scale, quantum effects should become important and prevent true singularities. Maybe the core is a tiny but finite region of incredibly dense quantum foam. But we don't have the math to describe it yet. The singularity paradox is a giant sign saying our physics is incomplete. There's something fundamental we're missing. Here's a more technical one that goes to the heart of how we think about black hole horizons. It's called the black hole complementarity principle, and it was proposed as a way to resolve the information paradox. The idea is that two different observers can have complementary but contradictory descriptions of the same event, and both are correct. An observer falling into a black hole sees nothing special at the horizon and carries information into the interior. An observer staying outside sees the information encoded on the horizon and eventually released in Hawking radiation. Both descriptions are complete and self-consistent, but they're incompatible. You can't combine them into one story. This is called complementarity, borrowing from quantum mechanics where particles can be described as waves or particles depending on the experiment. The paradox is that it seems to violate a basic principle of physics that there should be one objective reality. How can information be both inside the black hole and on the surface? The answer, according to complementarity, is that no single observer can verify both. The infalling observer can't communicate with the outside after crossing the horizon, so the contradiction never becomes observable. It's a radical idea. It says reality itself is observer-dependent in a deep way. Not just what you see, but what actually exists. And a lot of physicists are uncomfortable with that. Let's switch gears to something that might not even exist. The naked singularity problem. We've talked about singularities hidden inside black holes, safe behind event horizons. But what if you could have a singularity without a horizon? A naked singularity, exposed to the universe, visible from the outside. This would be catastrophic for physics. Singularities are places where our laws break down. If they're hidden behind horizons, that's okay, we can't see them or interact with them. But a naked singularity would allow information and matter to escape from a place where physics doesn't work. Causality could break down. Predictability would be lost. You could have effects without causes. Most physicists believe this can't happen. There's a conjecture called cosmic censorship that says nature always covers singularities with event horizons. Every singularity comes dressed in a black hole. But we don't have a proof. Some exotic collapse scenarios might produce naked singularities. Rotating or charged black holes, taken to extremes, have singularities that might be visible. The paradox is that general relativity allows them mathematically, but accepting them would mean accepting that the universe can have visible regions where physics stops working. So either cosmic censorship is true and some mechanism always prevents naked singularities, or they can exist and our entire framework is in trouble. That brings us directly to the conjecture I just mentioned, Penrose's cosmic censorship hypothesis. Roger Penrose proposed that the universe protects itself from naked singularities. Whenever a singularity forms, nature ensures it's hidden behind an event horizon. Weak cosmic censorship says this is true for observers far away. Strong cosmic censorship says it's true for all observers, even those falling in. Here's the paradox. We have no proof that cosmic censorship is true. It's a hypothesis, a conjecture, something we believe because the alternative is too disturbing. And there are situations where it might be violated. Certain rotating black holes, if spun up fast enough, might shed their horizons. Some mathematical solutions to Einstein's equations allow naked singularities. Computer simulations sometimes produce them in exotic scenarios. So is cosmic censorship a real law of nature or just wishful thinking? If it's true, what mechanism enforces it? Does the universe actually care about hiding singularities from us? And if it's false, what does that mean for the predictability of physics? Penrose's conjecture is beautiful and reassuring, but we don't know if it's right. It's a paradox of hope versus proof. Now let's talk about a strange intersection of thermodynamics and black holes. The black hole entropy paradox. In the 1970s, Jacob Bekenstein realized that black holes have entropy, a measure of disorder or hidden information. Weirdly, the entropy is proportional to the surface area of the event horizon, not the volume. For normal objects, entropy depends on volume, how much stuff is inside. But for black holes, it's all about the surface. This led to the holographic principle, the idea that all the information inside a volume can be encoded on its boundary. It's like a 3D image encoded in a 2D hologram. Here's the paradox. Why is entropy tied to area? What does that mean physically? And if a black hole has entropy, it has temperature. Hawking radiation confirmed this. Black holes are thermodynamic objects, but they're also the simplest objects in the universe according to the no-hair theorem. How can something with no distinguishing features have enormous entropy? Where is the information stored? On the horizon somehow? Inside? The answer seems to involve quantum gravity and is related to the information paradox. Black hole entropy suggests that spacetime itself, at the Planck scale, has microscopic states we don't understand. The paradox is that thermodynamics and gravity are deeply connected in ways we're only beginning to glimpse. Let's close this segment with one of the most mind-bending ideas in recent theoretical physics. It's called the ER equals EPR conjecture, and it connects wormholes with quantum entanglement. ER refers to Einstein-Rosen bridges, which are wormholes, theoretical tunnels through spacetime connecting distant regions. EPR refers to Einstein-Podolsky-Rosen pairs, quantum entangled particles. The conjecture, proposed by physicists including Juan Maldacena, says these two things are the same. When two particles are entangled, they're connected by a tiny wormhole. You can't travel through it or send information, but the geometric connection is real. This is wild. It suggests that quantum entanglement, this spooky action at a distance that Einstein hated, is actually a geometric feature of spacetime. Space and quantum mechanics are unified at a deep level. Here's the paradox. If entanglement creates wormholes, and entanglement is everywhere in quantum systems, does that mean spacetime is stitched together by countless microscopic wormholes? Is space itself an emergent property of quantum entanglement? Some versions of quantum gravity suggest exactly this. Space might not be fundamental. It might be woven from entanglement. ER equals EPR is still speculative, but if it's true, it would revolutionize how we think about both black holes and the fabric of reality itself. Wormholes and entanglement, geometry and quantum mechanics, all the same thing. Beautiful and baffling. And that's our journey into the darkest, densest, most extreme paradoxes in the universe. Black holes push everything to the limit. Information, entropy, space-time, quantum mechanics, they're cosmic laboratories where our best theories collide and sometimes break. But we've still got 2 more segments to go. Next up, we're going to explore something even stranger in a way. Not extreme physics, but extreme possibilities. Parallel worlds, alternate realities, and the paradoxes that come from asking, what if there's more than one universe? Let's talk about the multiverse. All right, we've stared into black holes and survived. Now let's ask an even bigger question. What if our universe isn't the only one? What if everything we can see, all the galaxies and stars in space stretching billions of light years in every direction, is just one bubble in an infinite foam of universes? The multiverse. It sounds like science fiction, but it keeps popping up in serious physics. Quantum mechanics suggests it, inflation theory predicts it, string theory requires it. And once you start taking the idea seriously, you run into paradoxes that make everything we've talked about so far look simple. Because if every possibility happens somewhere, if every quantum outcome spawns a new reality, if there are infinite versions of you making infinite choices, then what does it mean to be you? What does probability mean? Why is our universe so special? Or is it? These 11 paradoxes explore the dizzying implications of parallel worlds and alternate realities. Let's step through the looking glass and see what happens when one universe isn't enough. We'll start with one of the most unsettling observations in all of cosmology, something called the fine-tuning paradox. Here's the thing. The fundamental constants of nature, things like the strength of gravity, the mass of the electron, the cosmological constant, they all seem to be set to very precise values that allow life to exist. Change any of them by even a small percentage, and the universe becomes sterile. Stars wouldn't form, or they'd burn out instantly. Atoms wouldn't be stable. Chemistry wouldn't work. Complex structures couldn't exist. We live in a universe that seems incredibly fine-tuned for our existence. But why? There are 3 main answers. 1, it's just a coincidence. We won the cosmic lottery. 2, there's some deeper physical principle we don't understand that requires the constants to have these values. Or 3, there are countless universes with different constants, and we obviously find ourselves in one where life is possible. That's the multiverse answer. If there are infinite universes with every possible combination of constants, then some will have the right conditions for life, and that's where observers will emerge to ask the question. The fine-tuning paradox isn't proof of the multiverse, but it's one of the strongest arguments for it. The alternative is accepting that we're extraordinarily lucky, or that the universe was designed. Either way, it's deeply strange. That leads us directly into the next big idea, something philosophers and physicists call the anthropic principle paradox. The weak anthropic principle just says that we observe the properties we do because if they were different, we wouldn't be here to observe anything. It's a tautology, but a useful one. The strong anthropic principle goes further and suggests the universe must have properties that allow observers to emerge. Some interpret this as meaning consciousness plays a fundamental role in the universe, which gets weird fast. Here's the paradox. The anthropic principle explains fine-tuning but feels circular. We exist, therefore the universe allows us to exist. That's not a predictive scientific statement. It doesn't tell us what the constant should be, only why we shouldn't be surprised they allow life. Some physicists hate anthropic reasoning because it seems to give up on finding deeper explanations. Others embrace it, especially in the context of the multiverse. If there are infinite universes, anthropic selection is just statistics. We're in a life-friendly universe for the same reason fish find themselves in water, but it still feels unsatisfying. Are we explaining the universe, or just explaining our perspective? The anthropic principle walks the line between profound insight and empty truism, and which side it falls on depends on whether the multiverse is real. Now let's dive into the interpretation of quantum mechanics that takes the multiverse most seriously. It's called the many worlds interpretation, and it's both elegant and completely insane. Proposed by Hugh Everett in the 1950s, it says that every quantum measurement doesn't collapse the wave function. Instead, the universe splits. Every possible outcome happens, each in its own branch of reality. When you measure a particle's spin, the universe branches into one where it's up and one where it's down. Both are real. Both continue existing. You just experience one branch. This means every choice, every quantum event, every possibility creates new universes. The number of parallel worlds is constantly exploding, growing exponentially every instant. Here's the paradox. If all branches are real, why do we only experience one? What determines which branch you're in? And if every possibility happens, does choice even matter? Are there infinite copies of you experiencing every possible life? Many Worlds solves the measurement problem elegantly. No collapse, no special role for observers, just deterministic wave function evolution. But the price is accepting that reality is unimaginably vast, constantly branching, and that your decisions don't determine outcomes, they just determine which branch you experience. It's philosophically disturbing, even as it's mathematically clean. And we have no way to prove or disprove it. Next up is something darker and more troubling. A thought experiment known as the doomsday argument. It uses probability and anthropic reasoning to predict when humanity will go extinct, and the answer is uncomfortably soon. Here's the logic. Assume you're a random human selected from all humans who will ever live. If humanity lasts millions of years and trillions of people are born, you're incredibly early in human history. Statistically unlikely. But if humanity goes extinct relatively soon, with only billions more people to be born, then being alive now is more typical. The doomsday argument calculates that with 50% probability, we're in the last half of all humans who will ever exist. Given about 100 billion people have lived so far, that suggests humanity might not have much time left. Here's the paradox. This reasoning feels wrong. How can your birth order tell you anything about the future? But the statistical logic is hard to refute. Some say the argument fails because you can't treat yourself as a random sample. Others say it's valid but depressing. There are ways to escape the conclusion, like assuming humanity spreads to the stars and creates trillions of descendants, making us early but not impossibly so. But the doomsday argument is a stark example of how anthropic reasoning and probability can lead to disturbing places. It's a paradox about our place in time and whether we can predict the future from our position in it. Let's shift to something that's pure thought experiment but reveals deep issues in probability. It's called the simulation hypothesis paradox, though it's related to an older idea going back to Descartes. The modern version goes like this. If it's possible to create simulated realities, conscious beings living in computer-generated worlds, then advanced civilizations would probably create many such simulations. Maybe for research, entertainment, or just because they can. If many simulations exist for every one base reality, then statistically, you're more likely to be in a simulation than in the original universe. In fact, the odds could be billions to one that you're simulated. This is the simulation hypothesis, popularized by philosopher Nick Bostrom. Here's the paradox. If we're in a simulation, what does that mean? Is the physics we study just the rules of the program? Can the simulators intervene? Is there a reality outside the simulation, and if so, is that one also simulated? You get an infinite regress. Simulations within simulations, turtles all the way down. Some argue this means at least one reality must be base, non-simulated. Others say maybe it's simulations all the way and there is no base reality. The simulation hypothesis isn't testable in the normal sense, but it raises real questions about the nature of existence and whether we can trust our perceptions. It's the multiverse idea taken to a digital extreme. Here's a probability puzzle that philosophers love to argue about. It's known as the Sleeping Beauty problem, and it goes like this. Sleeping Beauty volunteers for an experiment. She'll be put to sleep on Sunday. A fair coin is flipped. If heads, she's woken on Monday, interviewed, and put back to sleep with amnesia of the interview. If tails, she's woken on Monday, interviewed, put to sleep with amnesia, then woken again on Tuesday and interviewed again, with no memory of Monday. Each time she wakes, she's asked, "What's your credence that the coin came up heads?" Think about it. The coin is fair, 50-50 odds. But if it's tails, she wakes twice. If it's heads, only once. So when she wakes, is the probability of heads 1/2 or 1/3? Halfers say it's 1/2 because the coin is fair and she has no new information. Thirders say it's 1/3 because she's twice as likely to be in a tails waking than a heads waking. Both arguments are logically coherent. The paradox reveals deep issues in how probability works with self-locating information and amnesia. In the multiverse context, this is relevant because if there are multiple copies of you in different branches, how do you assign probability to which one you are? The Sleeping Beauty problem is simple to state but has no agreed-upon answer, and it shows how tricky probability becomes when multiple identical or nearly identical observers exist. Let's get darker again with something called quantum suicide, a thought experiment that takes many worlds to an extreme. Imagine you set up a quantum suicide machine. Every second, it measures a particle in superposition. If the result is one outcome, you live. If it's the other, the machine kills you instantly. In many worlds, the universe branches each time. In half the branches, you die. In half, you survive. From your subjective experience, you always find yourself in a branch where you survived, because the dead branches contain no consciousness to experience. So you run the machine 10 times, 1,000 branches where you died, one branch where you survived 10 times in a row, but you only experience the survivor branch. From your perspective, you're immortal. The machine never kills you, even though the odds are 1,000 to 1 against you. Here's the paradox. Does this prove many worlds? Should you be willing to test it? Obviously, to everyone else, you almost certainly died. But from your point of view, you always survive, no matter the odds. Quantum suicide is deeply controversial. Some say it's a valid test of many worlds. Others say it's meaningless because the dead branches can't report back. And ethically, it's horrifying. Because even if you subjectively survive, you've created countless branches of grieving loved ones. It's a paradox that treats consciousness and probability in the multiverse as deadly serious questions. Moving on to something equally strange in the realm of cosmology, we have the Boltzmann multiverse paradox. We talked about Boltzmann brains earlier, those random fluctuations that could produce conscious observers. Now extend that to the multiverse. In an eternally inflating universe, where different regions have different properties, quantum fluctuations can produce anything given enough time and space. Entire universes, complete with galaxies and histories, could fluctuate into existence. But statistically, smaller fluctuations are more common than larger ones. A single galaxy is more likely than a universe full of galaxies. A solar system more likely than a galaxy. And a lone brain more likely than a solar system. So if the multiverse is eternal and infinite, most observers should be Boltzmann brains, or minimal fluctuations, not normal evolved beings in vast structured universes. But we observe a huge universe. That seems unlikely. Here's the paradox. Either our cosmological models are wrong, or we're incredibly atypical observers, or there's some selection effect we don't understand. Some physicists use this to rule out eternal inflation models. If your theory predicts most observers are random phantoms, it's probably wrong. The Boltzmann multiverse paradox shows that infinity is dangerous. Given infinite chances, the improbable becomes inevitable, and the most common outcomes might be the strangest. Let's talk about string theory and the paradox it creates. String theory is an attempt to unify quantum mechanics and gravity by proposing that fundamental particles are tiny vibrating strings. It's elegant mathematically, but it has a problem. The theory has something like 10 to the 500th power possible solutions, each corresponding to a different possible universe with different physical laws and constants. This is called the string theory landscape. Here's the paradox. If string theory is correct, it doesn't predict one universe. It predicts a vast multiverse where every possible configuration exists somewhere. That makes the theory almost unfalsifiable. You can't predict what the constants should be because they're different in different universes. We just happen to live in one that allows life. This is the string theory landscape paradox. On one hand, it neatly explains fine-tuning through the multiverse. On the other hand, it sacrifices predictive power. Some physicists embrace the landscape and say cosmology becomes anthropic and statistical. Others see it as a failure, a sign that string theory isn't really explaining anything. The paradox is that our most ambitious attempt at a theory of everything might actually predict everything, and therefore nothing. It's beautiful math that might not be physics, and we don't know if we'll ever be able to test it. Now we get into some really technical territory with something called the measure problem in cosmology. If the multiverse is infinite, with infinitely many regions and infinitely many observers, how do you calculate probabilities? Normally, probability is the number of favorable outcomes divided by total outcomes. But infinity divided by infinity is undefined. You can get any answer depending on how you count. For example, in an infinite universe, there are infinitely many copies of you. There are also infinitely many copies of you who made different choices. Which infinity is bigger? It depends on how you measure. Do you count by volume? By number of observers? By time? Different measures give different answers, and there's no objective way to choose. This is the measure problem, and it's a huge issue in multiverse cosmology. Without a measure, you can't make predictions. You can't say which observations are typical or atypical. The paradox is that infinity breaks probability. Every event happens infinitely often. Every outcome is realized infinitely many times. So what does it mean to say something is likely or unlikely? Cosmologists have proposed various measures, but none are universally accepted. The measure problem is a sign that our mathematical tools struggle with actual infinity. And it might mean the multiverse, even if real, is beyond our ability to describe probabilistically. Let's close out this segment with one more brainbender from cosmology. It's called eternal inflation, and it comes with its own set of paradoxes. The idea is that inflation, that rapid expansion right after the Big Bang, never really ended. It's still happening in most of the universe. Our observable universe is just a pocket where inflation stopped and normal expansion took over. But elsewhere, space is still inflating exponentially, and within that inflating space, new pockets constantly form. Each pocket is a universe with potentially different laws. Inflation is eternal to the future, constantly creating new universes forever. Here's the paradox. If inflation is eternal, it produces infinite space and infinite universes. That brings back all the problems we've discussed. Infinite copies of you, the measure problem, Boltzmann brains, all of it. But there's another issue. Is inflation eternal to the past? Most models say no. There was a beginning, a first moment of inflation. But some physicists argue that if inflation is eternal to the future, it might be eternal to the past, too, meaning no beginning. And if there's no beginning, where did the universe come from? The eternal inflation paradox is about whether the multiverse has an origin, or whether it's turtles all the way down in time as well as space. Its existence itself becoming paradoxical. And it's a reminder that the biggest question, why is there something rather than nothing, might not have an answer. Or the answer might be that there's always been something, eternally creating more somethings forever. And that brings us to the end of our tour through multiverse and parallel reality paradoxes. 11 mind-bending ideas that take the universe we know and multiply it into infinity. Fine-tuned constants, branching realities, simulated worlds, and eternal creation. The multiverse isn't proven, but it keeps emerging from our best theories. And with it comes a whole new set of paradoxes about identity, probability, and existence itself. But we've got one more segment left. We've gone through time, infinity, quantum mechanics, cosmology, black holes, and the multiverse. Now let's finish with something different. Paradoxes that are less about physics and more about logic, language, and the very structure of thought. Let's dive into the existential and philosophical paradoxes that have haunted human minds for millennia. We've traveled through time, infinity, quantum weirdness, cosmic mysteries, black holes, and parallel universes. Now, for our final segment, let's step back and look at something even more fundamental. Not the physics of reality, but the logic of reality. the paradoxes that emerge from language, thought, and the very structure of reasoning itself. These are ancient problems, some going back thousands of years, but they're just as relevant in space and cosmology as they are in philosophy. Because when you're trying to understand the universe, you're using logic, language, and concepts. And if those tools themselves contain paradoxes, then maybe the universe isn't the problem. Maybe it's our minds. These 11 paradoxes are about identity, truth, definition, and existence. They're the questions that keep philosophers awake at night and make physicists wonder if math itself might be broken. So let's finish this journey with the deepest, strangest, most existential paradoxes we can find. Get comfortable. This is the home stretch. Let's start with a classic that goes all the way back to ancient Greece but has cosmic implications. It's called the Ship of Theseus. Here's the thought experiment. Theseus has a ship. Over time, planks of wood rot and get replaced. First one plank, then another, then the sail, then the mast. Eventually, every single piece of the original ship has been replaced. Is it still the same ship? Most people say yes, it's still the Ship of Theseus. It's had continuous existence, just with maintenance. But here's the twist. What if someone collected all the old planks and rebuilt the original ship from them? Now you have two ships. One with continuity of form and function, one with continuity of material. Which is the real Ship of Theseus? Now apply this to space. Every atom in your body is replaced over time. You're not made of the same matter you were 7 years ago. Are you still you? What about a star? Stars burn hydrogen, fuse it into helium, lose mass through stellar wind. Is a star at the end of its life the same star as when it formed? What about galaxies that merge? Two galaxies collide and become one. Is the result a new galaxy or a continuation of both? The Ship of Theseus paradox is about identity over time, and it suggests that identity might be a human concept we impose on the universe, not something the universe actually has. Continuity is a story we tell. The universe just is. All right, switching gears to a logical puzzle that's delightfully strange. This one's called the unexpected hanging paradox. A judge tells a condemned prisoner, "You will be hanged at noon on one of the 5 days next week, but you won't know which day until the morning of the hanging. The hanging will be a surprise." The prisoner thinks about this and reasons as follows. "I can't be hanged on Friday, because if I'm still alive Thursday night, I'll know it's Friday, so it won't be a surprise. So Friday is out. But if Friday is eliminated, I can't be hanged on Thursday either, because if I'm alive Wednesday night and Friday is impossible, I'll know it's Thursday. So Thursday is out. By the same reasoning, Wednesday, Tuesday, and Monday are all eliminated. The prisoner concludes he can't be hanged at all. Then Wednesday morning, the guards come. The prisoner is shocked. He didn't expect it. The hanging proceeds exactly as the judge said. Here's the paradox. The prisoner's logic seems sound, but the conclusion is obviously wrong. Where's the flaw? Logicians have debated this for decades. Some say the error is in assuming you can work backward. Others say the judge's statement is self-referential and breaks logical rules. The paradox shows that reasoning about your own knowledge and future surprises can lead to contradictions. It's relevant in physics when we think about prediction and determinism. Can you predict your own future choices? If you can, are they really choices? The unexpected hanging messes with self-reference and knowledge in ways that still aren't fully resolved. Here's one that combines free will, prediction, and game theory into a beautiful knot. It's called Newcomb's paradox. You're presented with two boxes. Box A is transparent and contains $1,000. Box B is opaque and contains either $1 million or nothing. You have two choices. Take both boxes or take only box B. Here's the catch. There's a predictor, maybe a super-intelligent alien or a godlike computer, that predicted your choice yesterday. If it predicted you'd take both boxes, it left box B empty. If it predicted you'd take only box B, it put $1 million in it. The predictor has been right 1,000 times before. It's never wrong. What do you do? Standard decision theory says take both boxes. The money is already there or not. Your choice now can't change the past. Taking both gets you at least $1,000. maybe 1,000,000, and 1,000. But if the predictor is always right, people who take both boxes get 1,000, and people who take only box B get 1,000,000. So you should take only box B. Both arguments seem correct, but they give opposite answers. Newcomb's paradox has split philosophers and decision theorists into camps for 50 years. It's about whether the future can be perfectly predictable and what rationality means in the face of perfect prediction. In a deterministic universe, or in many worlds where all branches happen, does choice even exist? Newcomb's paradox doesn't have a universally accepted answer, and that's what makes it so fascinating. Let's go really fundamental now with something called the liar's paradox. It's ancient, simple, and still unsolved. Here's the statement. This sentence is false. Think about it. If the sentence is true, then it's false, as it claims. But if it's false, then it's actually true. It can't be consistently true or false. It's a contradiction. You might think this is just wordplay, but it's deeper than that. The liar's paradox shows that self-referential statements can break logic, and this matters in mathematics and computer science. Gödel's incompleteness theorems, one of the most important results in logic, are basically a formalized version of the liar's paradox. Gödel showed that any sufficiently complex logical system contains statements that are true but unprovable within that system. There are truths that mathematics can't reach using its own rules. In cosmology, this raises questions. Is the universe logically consistent? Can we fully describe it with mathematics, or are there true things about reality that are beyond proof? If our logical tools contain paradoxes, can we trust them to understand existence? The liar's paradox is a crack in the foundation of reasoning, and it's never been fully repaired. We work around it, but it's always there, reminding us that language and logic have limits. That brings us to one of the most famous paradoxes in mathematics, discovered by Bertrand Russell in the early 20th century. It's called Russell's paradox, and it shook the foundations of set theory. Here's how it goes. Consider the set of all sets that do not contain themselves. Most sets don't contain themselves. The set of all apples doesn't contain itself because it's not an apple, it's a set. So far, so good. Now, does the set of all sets that don't contain themselves contain itself? If it does, then by definition it shouldn't, because it's the set of sets that don't contain themselves. But if it doesn't contain itself, then it meets the criteria to be in the set, so it should contain itself. Contradiction. Russell's paradox showed that naive set theory was broken. You can't just assume any collection forms a valid set. Mathematicians had to rebuild the foundations of mathematics with more careful rules to avoid this kind of self-reference. Here's why it matters cosmologically. If we use set theory and logic to describe the universe, and those tools have paradoxes, what does that say about our descriptions? Is the universe itself paradoxical, or just our mathematical language? Russell's paradox is a reminder that even math, our most rigorous tool, had to be debugged. And maybe it still has bugs we haven't found. There's a simpler, more intuitive version of Russell's paradox that's often told as a story. It's called the barber paradox. Imagine a town with one barber. The barber shaves all, and only those men in town who do not shave themselves. Simple enough. Now the question. Does the barber shave himself? If he does shave himself, then he's a man who shaves himself, so according to the rule, he shouldn't shave himself. But if he doesn't shave himself, then he's a man who doesn't shave himself, so according to the rule, the barber should shave him. But he is the barber. Contradiction. The barber paradox is just Russell's paradox in everyday language. It shows that certain rules, when applied to themselves, create logical impossibilities. The resolution is that such a barber cannot exist. The scenario is self-contradictory, but this raises interesting questions about rules and laws in the universe. Are there situations in physics that are logically impossible? Can the universe contain self-referential structures that break their own rules? Probably not, but the barber paradox shows how easily language can construct impossibilities. We have to be careful that our theories don't accidentally do the same thing. Just because we can say something doesn't mean it can exist. Now, here's a really strange one from logic that's less well known but deeply weird. It's called Curry's paradox. It goes like this. Consider the sentence, if this sentence is true, then the universe will explode. Sounds harmless, right? But watch what happens. Assume the sentence is true. Then the if-then statement holds, so the universe explodes. But we derived that just by assuming the sentence is true. So the sentence is true. And if it's true, the universe explodes. We just proved, using pure logic, that the universe will explode. Obviously, that's wrong. So where's the error? Curry's paradox is a self-referential conditional that lets you prove anything. If this sentence is true, then 2 plus 2 equals 5. By the same reasoning, you can prove 2 plus 2 equals 5. It's a more dangerous version of the liar's paradox because it doesn't rely on negation. It works with simple implication. Logicians have developed systems to avoid Curry's paradox, usually by restricting self-reference or how conditionals work, but it's a reminder that our basic logical connectives, things like if-then, can misbehave in weird cases. In a universe governed by logical laws, Curry's paradox suggests we need to be very careful about how those laws are structured. Self-reference is dangerous. The universe talking about itself can break logic. Let's move to something more concrete but equally puzzling. It's called the Sorites paradox, also known as the heap problem. It's about vague predicates and boundaries. Here's the setup. You have a heap of sand. If you remove one grain, it's still a heap. Remove another grain, still a heap. You can keep removing grains one at a time, and at each step, it seems like it's still a heap. But eventually, you're down to one grain. That's not a heap. So where did it stop being a heap? After which grain? There's no clear answer. One grain can't make the difference between a heap and not a heap. But somewhere the transition happened. The Sorites paradox applies to any vague concept. When does a cluster of stars become a galaxy? When does a collection of molecules become alive? When does a fertilized egg become a person? We use categories and definitions, but reality is continuous. Boundaries are fuzzy. In space, this matters when we classify objects. Is Pluto a planet? When does a large asteroid become a dwarf planet? When does a brown dwarf become a star? We make cutoffs, but they're somewhat arbitrary. The universe doesn't come with labels. We impose them. The Sorites paradox shows that language and reality don't perfectly match. We think in discrete categories. The universe exists in smooth gradients. And the gap between the two is where paradoxes live. Here's a paradox about belief and probability that's surprisingly tricky. It's called the lottery paradox. Imagine a lottery with 1,000,000 tickets. You own one ticket. It's rational to believe your ticket will lose, right? The odds are 999,999 to 1 against you. In fact, for every single ticket, it's rational to believe that specific ticket will lose.